All right. Hello, AP Physics 1 students. I hope you're doing well. I'm going to change the brightness of this. Hope you guys are doing well. And I hope you had a good spring break. I mentioned in the news today that I was playing a little Animal Crossing, and I know I've got some Animal Crossing fans in this class. So, yeah, it's a pretty fun game. One thing I'm really sad about is I forgot to play yesterday, so I missed Bunny Day. So I don't know. I didn't get to see everyone in their cute bunny costumes for Bunny Day yesterday. So that was a bummer. Hey, Ethan. So what are we going to do today? We just got a couple of topics left before we know everything that's going to be on the AP exam. So next week, I'm going to be starting to review. And yeah, so what are we going to talk about today? Well, salutations, Jaden. So what are we talking about today? Let's suppose I had a graph of y versus x. And maybe the graph looks like this. Like that. I don't know. Wouldn't it be nice? Now, our brains are not very good at deciphering wiggly lines, okay, or curved lines. But our brains are really good at understanding straight lines, okay? So wouldn't it be nice if we could define new variables, y squiggle and x squiggle, such that this looks like a straight line now? Okay. Wouldn't it be nice if we could do that? And what would be the meaning of the slope? Okay. Because basically what humans are good at is making line graphs and calculating the slope. Okay. So the topic, so this is just sort of a general skill that students should know. And actually, I think this is a really important skill that is under-taught in high school. So you guys are going to get a leg up by learning this lesson today. So the title of this lesson is Linearizing a Graph. How do you take a graph that is not a line and you make it look like a line? Okay. So for example, so we'll start off, we're just going to do a series of examples. Okay. I don't know if you guys can hear that, but that's Hazel snoring. She's snoring real loud. Here, I'll show you guys Hazel. Why is this? Hazel. Oh, my. Come on, Hazel. Here's Hazel. How you do, Hazel? Okay, I'm putting her back. Okay. So, where was I? There we go. So what if I wanted to do a look at the graph delta x equals 1/2 at squared. So this is position versus time for a position versus time for uniformly accelerated motion. So what would this graph look like if we were going to graph displacement versus time? Well, see how it's delta x equals 1/2 at squared. So it's going to look like a parabola. Looks like this. That's not a straight line. So what we want to do is see if we can redefine variables so that this looks like a straight line. Okay? So I have to figure out what is my y squiggle and what's my x squiggle. So I'm going to let my y squiggle be equal to delta x. Okay? And I'm going to let my x squiggle be t squared. All right? So if I write, so I'm redefining some variables, y squiggle and x squiggle. If I rewrite my equation in that form, then it's going to be y squiggle equals 1/2 a times x squiggle. Okay? Now, why do I say that that's going to be the equation of a line? Well, the equation of a line is y equals mx. So see how it's y equals constant times x. So this is going to look like a straight line. Y squiggle, x squiggle, it's going to be a straight line. And what is the slope of that line going to represent? Well, the slope is the number that multiplies x squiggle. So the slope is going to be 1/2 the acceleration. So we've taken a bendy graph and we've turned it into a linear graph. Now, here's another thing. There's actually more than one way to do this. Okay. Let me give you an example of another way to do this. What if I took my equation and I defined y squiggle squiggle to be delta x over t, and I let x squiggle squiggle equals t. Okay? What if I did that? Well, if I took my equation delta x equals 1/2 at squared, and what if I divided both sides by t? Then I would have delta x over t equals 1/2 a times t. So notice how this is y squiggle squiggle, and then equals 1/2 a, and then t is just x squiggle squiggle. All right. So if I were to do a graph of, see how this is the equation of a line. It's y equals a number times x. So if I were to do a graph of y squiggle squiggle times x squiggle squiggle, it's going to look like a straight line. The slope of that is a over 2. Okay? So there's multiple ways to take a bendy graph and turn it into a straight line graph. But see how the slope is related to the acceleration? We would never have our y squiggle or our x squiggle depend on the acceleration. Why is that? It's because the acceleration is what we're trying to figure out. Okay? So we didn't take a bunch of points with different accelerations. We took a bunch of points at different times. So it doesn't make sense to put different values for the acceleration. There's only one value for the acceleration. Okay? So let me give you an example of a no-no. You might think that this makes sense, but this is a no-no. A no-no might be, what if I let y squiggle equals delta x, and then x squiggle equals the acceleration? What if I did that? Then what is my equation going to become? That means that my equation would be y squiggle equals t squared over 2 times x squiggle. So that looks like a straight line, but you can see that the slope of the line is t squared over 2. Now that just doesn't make any sense because time goes on, it changes, right? So you can't just have one value for time. All right, so this is a big no-no. All right, your x squiggle should only depend on, and your y squiggle should only depend on the original variables in the problem. Okay, so let's do another example. What if we had the law of the gravitational force? The law for the gravitational force is G m1 m2 over r squared. Okay, now the normal graph that you could make would be force versus distance. And we know that the force is really strong when the things are close together and really weak when they're far apart. So the force graph actually looks like this. Okay. So how could we take this and turn it into a line? All right. And here's the key. I'm going to write the gravitational force law as G m1 m2 times 1 over r squared. All right. So what if I let y squiggle equal force? And what if I let x squiggle be 1 over r squared? In that case, my equation would become y squiggle equals G m1 m2 times x squiggle. That's the equation of a line. So I've taken something that doesn't look like a straight line and I've turned it into a straight line. What would be the meaning of the slope of that line? The slope would be G m1 m2. Okay. Let me show you a different way of doing it. What if I rewrote the gravitational force equation as R equals, okay, R times 1 over G m1 m2 FR. Oops. 1 over F times R. Okay, so if you multiply this out, you can see that it's the same as the original gravitational force law. So what if I let y squiggle equals 1 over F times R and x squiggle equals R? Okay, in that case, this equation is going to become, see how this is just y squiggle. This is just x squiggle. And this is multiplying x squiggle. So we get 1 over G m1 m2. All right. So if we were to graph y squiggle versus x squiggle, in this case, it would be a straight line. And the slope of that line would be 1 over G m1 m2. Okay, so there's multiple ways to get a straight line depending on what you define your x squiggle to be and your y squiggle to be. We're going to do one more example. Let's do an example with Kepler's law. Okay. Kepler's law says gmt squared equals 4 pi squared r cubed. So just to remind you, m was the mass of the central body, t was the period of the orbit, r was the radius of the circular orbit. Okay? So how could we make this a straight line? Okay, because normally what you would do is you would do a graph of, say, period versus size, and that's not going to look like a straight line. So what if I defined y squiggle equals t squared, and then I define x squiggle equals r cubed? So what does the equation become in that case? It would become gm y squiggle equals 4 pi squared x squiggle. Simon, did you actually adopt a dog, or are you just being sarcastic? So then you have y squiggle equals 4 pi squared over gm times x squiggle. So that's the equation for a line. Oh my gosh. So we have y squiggle, x squiggle. It's a straight line. The slope of the straight line is the thing that multiplies x squiggle. It is 4 pi squared over gm. Okay? So we've taken Kepler's law and we've turned it into a line. If you like, I can give you one more example of a different way you could do Kepler's law. What if I defined y squiggle as, so this is a new example, r squared over t. And what if I defined x squiggle as t, actually, yeah, t over r? What if I did that? In that case, I could rewrite Kepler's law as gm times t over r equals 4 pi squared r squared over t. All right. So you can double check that if you multiply the t over, you get t squared. You multiply the r over, you get r cubed. So it's still the same relationship, just written in a weird way. T over r is x squiggle. R squared over t is y squiggle. And then I could divide both sides by 4 pi squared. I get gm over 4 pi squared times x squiggle equals y squiggle. So once again, I have made a straight line, y squiggle, x squiggle. The slope of the straight line is the thing that multiplies x squiggle. It's gm over 4 pi squared. All right. So this is a little bit tricky. I'll be honest. Students have a hard time with this. If you can get a hold of it, I guarantee you, if you're going to be an engineer or a scientist, it will have benefits for you. Okay. So, and it is on the AP exam. It's in one of the experimental analysis techniques, is you want to make a line instead of a curve for your graphs. Really good question. What is the application of this concept? Why should we make something a straight line? Straight lines, if you have a straight line, you can calculate the slope really easily. If you have a curved line, the slope is changing, okay? So it's really easy to calculate slope of a straight line. That's the reason why. So we want to try to relate our concepts to a straight line if possible, because then we can get the slope. So that's why. All right, that's my lesson for today, and I will see you tomorrow with another topic.